classification problem. I'm able to classify a group of item from milk, a group of item from sugar. I'm able to identify sugar from group of item. I'm able to identify coffee powder from group of items. So first I have learned so many classification as part of coffee making process. Then if it is for two people, how much milk I have to add is a regression problem. Because for one person, so much is the milk. For 5%, so much is the milk. I might have learned as part of the learning process. Now I have to make coffee for two people. How much of milk I have to take is a regression problem. So I take so much of milk, so much of sugar, so much of sweetener, whatever, sugar cane or whatever that sugar, white sugar or jaggery, whatever you want to add, you add, and make coffee out of it. Mix it in a proportion and serve it. It is all comes under regression problem. Okay, as an intelligence, what we learn in the process of making coffee is certain number of classifications, certain number of regressions. How much of milk, how much of sugar, how much of jaggery. All these things are part of your regression models that you have learned as part of coffee making. Since learning is quite natural to the human, we learn effortlessly. Whereas computers are dumb machines. They have very high capability of learning, but they are not self-learned. But if you write algorithms intelligent enough and ask the machine to learn, it's possible to make a machine to learn like human. People, discovered this fact and started working on it, and that area grows very well. You call that as machine learning, and you explicitly give the features and other stuff. Without giving features, you want system to learn by itself like human. You call that as a deep learning, DL. I put it as a red color circle, and superset of that is AI, artificial intelligence. So your artificial intelligence includes your machine learning and deep learning as inner part of this idea. Right. Why are we discussing all this? Because we want to learn machine learning. So we are doing this. There are three types of learning: supervised learning, unsupervised learning, and reinforced learning. Supervised learning is, a teacher will be there in front of you. He will be teaching you, and you will be learning. Okay, that's supervised learning. That means what? Your mother will be standing nearby and show a cow and tell that's a cow. You learn that animal is a cow. You learn. Unsupervised learning means there is nobody to teach you. You are in the forest, for example, and there are certain animals. Let's say elephant, very big in size, with some, there are 4 legs and 1 big drum, and you identify such animal. And there is another, let's say tiger or a lion, very little, compared to elephant, it is very small in size. And there are another group of animals, let's say cats, very, very, very small compared to elephant. And you yourself learn looking at their sizes, looking at their colors, looking at the appearances, based on certain factors. You yourself learn. Nobody has taught. But you don't know the names of them because nobody has taught you. But you know these kind of animals belong to one group. The tiger, lions may look alike, or you may classify them accordingly. Let's put them in one basket for time being. You say they're all part of one group. And cats, very, very tiny animals, small animals. Okay, and still you will be able to learn by yourself without being taught. Unsupervised learning. And reinforced learning is you learn something, you go to your teacher and then confirm what you have learned is right. Again, you do your job for some time, learn a little more, you go and confirm with your teacher what you are doing is right. Like kids, they do homework and then go and show to the parents, mommy, is it okay? What I'm doing is okay? Yeah, good baby, go. They go back and then continue. That's a reinforced learning, that you assure what you are learning is perfectly all right. That kind of learning is reinforced learning. Mostly, we will be using supervised learning. So we will not talk much about unsupervised learning. So there is a well-defined set of training data sets with the label. With the label means this data belongs to this particular class. And that means I know the label of that. If I, instead of simply giving animals, I also give if the height is so much, if the color is dusk in color, and uh, I give some more description, and then say if these parameters you are able to observe, then that is elephant. I also give the data in that column format, and the last column I say it is elephant. Similarly, same parameter, what are the values for lions? I give the label as lions. Similarly for cats. And such a data set is given to us. From that, we expect an algorithm to learn. Such a learning is supervised learning. Okay? So that's a supervised learning. What is the use of doing this machine learning, sir? All of us can resign our job, sit in home, make crores of money every day. If you know how to predict what's going to happen in another 1 hour, in another 1 day, in another 1 month on stock exchange, commodity exchange, or foreign exchange. Okay, that's the potential of that area. Stochastic time series modeling, if you're able to do, or that's not part of machine learning. But if you're able to do machine learning to predict what's going to be the stock market price or the crude oil price after 1 hour, you can accordingly put buy order, sell order, make huge amount of money sitting at your home. Okay, sales, targeted advertisements, analyze the buyer buying pattern. There are many applications for machine learning. So we are all mechanical engineers. We have come here early morning today to learn something about fault diagnosis. What is the use of that for us? What machine learning can do for us for condition monitoring? Okay, so condition monitoring, of course, many of you is not a new term that you are hearing it. Condition monitoring is monitoring the condition of the machine, whether it is healthy or if it is faulty. If it is healthy, of course, we don't bother much. Let's assume everything is going on smooth and be happy. If it is, if a component is faulty, if a machine is faulty, we wanted to know what is the nature of fault. Some more details about the fault we would like to know, so that we can prepare our mind for maintenance activities accordingly. So for that, we need information from the machines. That information may be a sound signal, it may be a vibration signal, it may be temperature, it may be pressure, depending upon the type of system that we are trying to monitor. It may be process monitoring, it may be a condition of a structure, so it may be a structural monitoring. Generally, condition can mean anything, a general term, whereas it can be structural monitoring, it may be process monitoring, any monitoring that you can do using these ideas. Depending upon the application, you choose the parameter which will help you to tell the status of that particular machine. Okay. So now, let's take, we want to do a civil engineering application. There is a bridge, and I wanted to know whether the bridge is in good condition or it is going to fail in the near future. So what do I do? When standard vehicle is going, let's say a lorry, empty lorry is going, I wanted to observe the vibration pattern of the bridge when the lorry is going. So I put an accelerometer, take the vibration signals, and then using the vibration signal, I wanted to tell whether the bridge is in good condition. There is a fan in my room. Okay, so there are bearings in that fans. I wanted to know those bearings are in good condition or it has become faulty. So I put an accelerometer and take vibration signal, and from the vibration signal, I wanted to analyze, learn, and label whether the present condition is safe, that is good condition, or that it is faulty. You need to give some alert. Such applications, you can use machine learning to do it. You have very well defined two states in this particular slide. This is a bin, a class called safe bin or safe class. You have another bin called an alert bin or alert class. So you have a classification. Whatever that is coming in, you classify it as safe or alert. So it becomes a classification problem. Machine learning algorithms will be able to help us in doing this classification problem. Similarly, your structural health monitoring of the aircraft structure, you have many more. Of course, bearing is my favorite one because I did PhD on that particular area from Amrita University. So you have bearing in good condition. It's a roller bearing. This is called inner race and there's an outer race. Here in the inner race there is a cut. We want to know is there such structural defect in the inner race. Similarly, you have outer race, there is a cut, and you want to know whether there is a problem with outer race. Here you have both. So these are all simulated faults, and you take signals from them. That will be the data that you will use for training the algorithm. Okay. So the machine learning is basically an algorithm which is capable of learning from the data. Okay. So fault diagnosis, I wanted to do fault diagnosis of bearing means I want to know the present status of the bearing using whether the bearing is in good condition or bearing is having a defect in the inner race or outer race or both inner race and outer race. So this is the kind of classification problem. I have 4 classes: good, inner race fault, outer race fault, both inner and outer race fault. So I have 4 different bins. The present incoming vibration signal I want to put in any one of these bins. Basically it is a classification problem. Just 1 minute I have. Sorry. Ana vanakana ana ஒரு கிளாஸ்ல இருக்கேன்னா நீங்க வீட்ல போய் வர்க் பார்த்துட்டே இருங்க வந்துறேன். ஹலோ. ஆனா நான் ஒரு கிளாஸ்ல இருக்கேன்னா நீங்க நீங்க வீட்டுக்கு வாங்க, வேலை பார்த்துட்டு இருங்க, நான் வந்துடுறேன். I'm sorry. I asked a carpenter to come. When you don't want them to come, they come at the right time. I have been calling him for a month, but I'm sorry. I'm in college now. Okay, so machine learning is basically now modeled as a classification problem where the incoming signal is put into any one of the 4 bits. What are the mechanical systems that we can think of? At least I have listed some of the systems which I have worked in: bearings, gearbox, wind turbine blades, lathes, or any machine tool for that matter, hydraulic brakes, centrifugal pumps, air compressor, misfire detection in IC engines, tire pressure monitoring, and many more. Of course, suspension system, steering system, any automobile component, because they're all very critical components. So all that you can do. You can also extend the same idea to interpret the status of the human for ECG signals, EEG signal, EMG signals, electrocardiogram, electroencephalogram, electromyogram. So all this are biomedical applications you can extend. But of course, our interest is not there, but we can extend this idea. So the technique is very versatile. So once you learn machine learning, you can apply that to variety of areas that you can think of. Right. So I have given an overview of like what is machine learning. We are going to talk more about that, and what is fault diagnostics, and we are going to merge these two. Now, what is that needed? The data that we observe as part of our experimental work can be of 2 types. One, a observation in the form of table. For example, the fluid mechanics lab, we go take X reading, Y reading, this we calculate, Pina contractor, discharge coefficient, something we do. We have a table of observation. From that we take, we arrive at some answers from that. That's one type of data that we get from experiments. Another type is a signal from a sensor. Okay. For example, the acoustic signal, the song that we sing, whatever I talk now will come as an audio signal. Vibration signals, sound signals, acoustic emission signals. They're all very high frequency signals using sensors that we will be able to get. You may not be able to put them in the form of a table. Okay, so that you have to store it as a signal only. So one is a more of a kind of a static signal. The other one is a bit of dynamic signal. What is meant by static signal? Of course, today, the temperature measurement is the order of the day. While coming inside the college, they take temperature from some part of the body. Earlier, they used to take from forehead. Now they are taking it from the hand, somewhere based on recommendation. So they take the temperature. They say 31 degrees Celsius is your temperature today. So we understand that is more or less static. No signal is going to be dynamic. More or less static for a period of time, you call those signals as static signals. What is signal means? What? Anything that gives some information. Okay. So if it is going to give some information, we are going to call it a signal. Static signal means for reasonable amount of time, if that is static, you call that as static signal. And dynamic signal varies very fast with respect to time, like sound waves, vibration signals, very high change in its magnitude with respect to time that we cannot tell a particular number for 1 minute of time, 10 minutes of time, that we may not be able to tell. Such signals are dynamic signals. When we deal with condition monitoring or fault diagnostics, mostly, at least for me, I have been using vibration signal. So vibration signal is a very high frequency signal that looks like this. Given a sample of that, this is exactly a good signal how it looks like for 8,000 samples. The x-axis is number of samples and y-axis is the amplitude. When bearing is in good condition, the signal looks like this. Similarly, when inner race is fault, the signal looks like this. Outer race is fault, the signal looks like this. And both faults are there, the signal looks like this. It's only a representative signal. Okay, there may be minor variation from signal to signal of the same class. But what you need to understand now is a very high dynamic nature of the signal. It's not very static. You cannot say now the vibration level is 2.1, 3, 3.1. Like that, one number you cannot simply assign. So you have to store this as a dynamic signal only in order to get full information from that sensor's output. So that's why it is signal. And telling any one particular number will not make any sense, will not give you information. If it is not giving information, it is not signal. So it has to give information. So you have to store the entire range of numbers, plot them as a graph, joining with a single line, you get a curve or waveform like this. This waveform, you call it a signal. And this varies very fast with respect to time, so you call it as dynamic signals. What is the problem with this dynamic signal? Especially systems from mechanical systems where we want to do the condition monitoring. You see, there is a galaxy, there is an universe, there is a planet. In the planet, in the atmosphere, there is an aeroplane that is flying. And there is a pilot, and the pilot sees a landscape. In the landscape, there is a stamp. In the stamp, there is a bus. In the bus, there is a ship. In the ship, there is a boy sitting with a book. The book has a girl's image with few houses on it, the toys of houses. In one of those houses, there's a door is open and there is a window. And through window, two kids are watching a cock and there is a tail for that cock. So, where is this planet? Where is this the tail of the cock? The time domain signal that we normally get from the sensor is something like this. What I have narrated in the a planet's bird's eye view. Whereas the information that we are looking for, the fault information that we are looking for, may be hidden inside that signal as a small information hidden inside that big amplitudes. Okay, so the record information is like the cocktail. The challenge is you have to identify the cocktail is there or not from the planet's figure. So you should have techniques, means by which you are able to decode that information from the vibration signal and eliminate the noise, zoom it if required, go and see whether it is there or not, you have to tell. So that is the challenge for you. So you definitely have to do necessary signal processing in order to achieve that particular job. What people used to do so far, let's say machine learning has not started. What people have been doing for 40 years from now, 40 years, last 40 years, what people were doing to do this job. People use Fourier analysis, Fourier transform. Okay, the fast way of computing this, we call it as fast Fourier transform. The famous acronym is FFT, fast Fourier transform. Mathematically, the continuous version and discrete version I have given. I'm not going to the details of the mathematics now. That's a course by itself. Fourier analysis itself is a course. We will not be able to do a justice on that. But what I wanted to bring out is, I hope your math teacher or even other professors would have taught you what is the function of Fourier transform. You have time domain signal f of t, and you multiply with something, integrate it from minus infinity to plus infinity, and then you do some normalization with the 2 pi. When you integrate it with respect to time from minus infinity to plus infinity, the time information is converted into what you see on the left hand side, omega, function of omega. You get frequency information. Okay, so the basic function of Fourier analysis is to convert the time domain signal f of t into a frequency domain signal f of omega. Okay, so this is for continuous version. The same thing for a discrete version. What you can do it using computers is the sigma version. Okay, this is integration. Integration is also a continuous summation by its meaning, and naturally we do continuous summation in the discrete form. So Fourier transform is to transform from one domain to another domain. You have two signals, you add it up, you get the, for illustration, you add it up, you get a combined signal, y is equal to a plus b. And this is the kind of signal which is noisy. You see, I have added some noise purposely. Random number is to add some noise. You have a 50 Hertz signal, you have 120 Hertz signal. Both signals I add along with some noise, I get this signal. Okay, if I do f of t, my power spectral density, the output of f of t will look like this, PSD. Okay, and how do I interpret this f of t? You see, at 50 Hertz, this is 40, this is 60, so you have 50 in between. At 50 Hertz, you get one peak, and here you have 120 Hertz, you have a peak. 120 Hertz, you have a peak. So here, when I look at the time domain, the x-axis is number of samples, y-axis is the amplitude. When I look at the time domain signal, I am not able to identify what are all the frequency components in this particular signal. Whereas here, I am able to identify that the signal has a 50 Hertz signal, a 120 Hertz signal. So the frequency content of that particular signal is brought out beautifully when we do f of t. And that's how people use f of t to do fault diagnosis. How to use f of t for finding faults in a signal? There is something called rotation characteristics frequency. What is characteristic frequency? For bearing, you have an analytical equation in terms of its component parameters, that if there is a fault in outer rays, at what frequency you will get a peak. You see, that's called outer rays frequency. F or is small n by 2, capital N by 60, 1 minus small d by capital D into cos beta. Small d is the diameter of the rolling element, capital D is the diameter of the bearing, and beta is contact angle, and n is the number of rolling elements. It can be ball or roller depending upon the type of bearing. So for you substitute all these values, you get some number at that particular hertz. You will find there is a peak if the outer rays is having some problem. If the outer rays has become faulty. Similarly, the blue color one shows inner rays fault. The yellow color one shows rolling element fault, and it is a cage fault. Cage fault is a kind of ring that holds these balls or rollers not coming out of the bearing. That part is called cage. If there is problem in that, it is called cage fault. Let's take an example. I took a bearing, 2-inch single row angular contact bearing with these dimensions. I substituted these values in the previous formula. I found out the normal rotational frequency is 29.1 Hertz. There will be a peak on that. That means bearing is normal. There is no other peak. Only 29.1 hertz. There is a peak. That means the bearing is normal. There is a peak at 29.1 hertz. Also, there is a peak at 140.7 hertz. That means in that particular bearing, the outer race is having some problem. If the height of the peak is high, the severity of the problem is high. If the peak is little small, the severity of the problem is small. Similarly, they observe other characteristic frequencies: 209 for inner race, 138 for roller bearing, 11 hertz for cage frequency. They look for the peaks at these specific frequencies. If there are peaks, they correspond to that particular problem. That's how they go ahead. Now, what is the problem with that? You look at the formula. There is a capital N, which is speed. There is a D, small d, capital D. Of course, capital D may not change much, but small d will change. N will change from time to time. N is RPM, the speed at which the rotary bearing is rotating. D is the diameter of the ball, the diameter of the rolling element. So, due to wear and tear, the D will change, the speed will change. Accordingly, the frequency components also will get shifted. I'm sorry. Any questions? So we need some technique which is capable of learning by itself.
Hello. Sir.
Yes.
Your PPT is not visible. Only we can see you.
PPT is not visible?
Yeah.
You change one more. PPT is visible, sir. PPT is visible, but not in full screen mode. Your camera only is in full
Sir,
screen.
you have to pin the that PPT screen. You have to pin that small thing.
Please, sir, you will get.
PPT is very fine, sir.
Super.
You pin the Sugumaran B presentation, that window.
Sir? Sir, now I am sharing my screen as such. Do you want me to stop sharing and share only the PPT?
Sir, it is visible, sir. Participants, you pin the presentation window.
Only presentation window. Okay. Because I have some demo also, so I thought full screen means you will be able to. Okay, present now. Present your window. I'll be presenting the chat. Is it now visible, sir?
No, sir, window is not visible now. Previously, it was visible.
Stop sharing. Sir, there are only 3 modes for me to present.
One, sir. Only one we found, sir.
No, present now option is gone for me. So I can't.
You just see the below, sir. There are present now.
Present now is deactivated now. Earlier it was active. Yeah, now it has come. 1 minute, sir.
Now you share, sir.
There are three options: entire screen, a window, a Chrome tab.
Windows, sir. You share Windows, sir.
Window. In that, I will choose the PPT, right, sir?
Yeah. You open the PPT, sir. Don't minimize. In that it will come, sir. Window.
Okay, sir. Is it visible, sir, now?
No, sir. Still it is not visible, sir.
Stop sharing. Present now is disabled.
Yes, sir.
Present now is disabled, sir.
Yes, sir. Now you click that present now, sir.
Present now is not active, sir. It is disabled.
Oh.
Now it is okay.
Now you click that and click Windows, sir.
Window.
Yeah, window. There you
And,
find some files are there. Your
Yeah,
PowerPoint is
my
there.
slideshow is there.
That you click, sir.
Yeah.
You share that window.
Is it visible, sir, now?
No, sir, it is not visible now. Huh? We will receive. So far, it is very clear, sir.
Now it is not visible, sir.
No, sir. Not visible, sir. Better, sir. Better you quit. Come again, sir, so that we can.
I have. Quit the meeting and come back, sir.
Yes, sir. You quit, sir, and come back, sir. Again, no problem.
All right, sir.
Sir, now it is visible, sir. Sugumaran, sir, now it is visible. Sir, Sir, now window is visible, sir. All participants to pin the presentation mode. Sir, you unmute your mic, sir.
Sugumaran sir, you,
Sir, sir, now window is very clear, sir.
okay
Yes,
sir.
sir.
Now,
I unmuted, sir.
okay sir.
Unmuted.
Now it's clear, sir.
Yes, sir. Window is very clear, sir.
Please continue, sir.
Right, sir.
You continue, sir.
Thank you, sir. Thank you. So you have certain examples for class A. You have certain examples for class B. So now a new sample is given to you. A new sample is given to you. How do you classify this new sample into class A or class B? Now the participant can look this. You can learn from these examples, whatever is on the top. Whatever you have learned, using that knowledge, you have to classify this into class A or class B. One way of learning is, you see left side bar is small, right side bar is high. So this matches with class B, so I can put it in class B. One way of learning. Another way of learning, if the right bar is below 5, that belongs to class A. If the right bar is above 5 or equal to 5, it is class B. That's another way of learning. Maybe you can similarly use this. If this is below 3.5 or equal to 3.5, this is class B. If it is above 3.5, it is class A. There are many other ways by which you can learn this classification. Okay. So each algorithm has its own way of learning. Similarly, here you can think of this is class A examples, this is class B. Now all samples are not small and big. Here the blue bar is big, here blue bar is small, whereas here blue bar is small, here blue bar is high, and vice versa. It's contradicting. It's not as simple as the previous problem. So how do we learn? We simply add these two numbers. 5 plus 6, 11. 5 plus 9, 14. 8 plus 12. 8 plus 4, 12. So here all above 10. Here you add 5 plus 3.1, 8.1, 8.5, 9.3. All below 10. So one way of learning this particular problem is you sum both the features. If it is less than 10, it is class A. If it is greater than 10, it is class B. That's how the machine learning algorithms learn. They find out some logic by which they classify class A as group A, class B as group B. Okay, and any new data you give, it applies the same algorithm and put in the respective bin. That's how the algorithms goes. So due to time, I skipped some of the slides. Now, what in machine learning, essentially, we do feature extraction, feature selection, and classification. This is the main theme of machine learning. We have vibration signal. Vibration signal, we cannot directly use it, most part of the algorithms. So generally, we do something called feature extraction. What is meant by feature extraction? I have a vibration signal. I may compute mean, median, kurtosis, skewness, other statistical parameters I will compute and call them as statistical features. I'll have some 12, 13 parameters I can extract. Okay. That means I will have some 12, 13 columns in Excel file. And if I have extracted these features from good bearing, I'll put as a last column as a class and I put the label as good. Now, what I have done is a feature extraction. Whereas vibration signal, if you look at it, since it is very high frequency signal, we will be acquiring the signal with very high sampling rate. For 1 second, there will be 12,000 samples. That means if you put that in Excel file, there will be 12,000 columns. Each value in one column, if you put it, there will be 12,000 columns. 12,001th column only you can put your label value. The algorithm will find it difficult to classify. Okay, so in order to reduce the dimension, you do feature extraction. You extract features. While doing feature extraction, we may not be very choosy. We just extract whatever possible features possible. Then feature selection, only certain features will be useful for classifying that particular problem. Those problems are called feature selection. Feature selection. Then we have reduced set. With the reduced set of features, you do this classification. Okay, so basically there are 3 operations: feature extraction, feature selection, and feature classification. For feature extraction, you have statistical features, histogram features, wavelet features. For classification, you have about 60 algorithms. I have named a few: J48 decision tree, K-star, IPK, support vector machine, proximal support vector machine, all that. There are many challenges. It's already time, so I'll just rush through a few slides and stop there. I have already planned to stop at 10:50, but it's already 10:20. 3 minutes, I'll stop the lecture. In data collection, you want to know whether you have collected sufficient data, whether the sampling rate, very challenging, to how to fix the sampling rate. What features will be best for your present problem? Statistical feature or histogram feature or wavelet features or any other feature. I told you there are more than 60 classifiers. Which classifier will be able to classify my problem well? There is no standard one algorithm which will work very well. So you have some samples, you do training, whether the training is sufficient, whether the number of samples that you have used for training is sufficient. All very challenging research questions. People still find answers. I am doing testing. I get some error. Whether that error is acceptable, whether the classification efficiency is okay, and we have a lot of features, and then we have feature selection. While choosing the features, whether I have to choose only 3 features or I have to choose 7 features. 3 features, I get so much classification accuracy. 7 features, I get so much classification accuracy. With small increase in classification accuracy, should I go for 7 features or little sacrifice in classification accuracy? I go with only 3 features. 3 features means the hardware requirement for implementing the algorithm is very less. So your cost of the device in which you are implementing that will be less. 3 features will be a good decision in certain applications. Whereas in certain applications, the accuracy is very important. You don't mind little extra cost, you don't mind little extra time, but accuracy of the answer is very important. You may go for 7 features. So look at the problem domain and importance of the problem and then decide. Say we have, we see some big stone is falling on somebody's head. We have seen. Will you be describing like this? Excuse me, gentlemen. 1000 kilogram of mass is approaching your head at the rate of 45.3 meter per second. Will you be interested in telling the accuracy of information there? What do you say? Hey man, look out there. There is a stone falling. Hey, move. Some shouting. That's what is important in that particular problem. Whereas you want to identify, you have some image, you have extracted some feature, identify and tell whether the person is having cancer or not. We don't mind extracting little more information. We don't mind waiting for another half an hour, no problem. But the answer that you are going to tell is very critical. The person is having cancer or not. Okay. So in certain places, the precision is important. In certain places, the significance, the quickness is important. They're all highly problem oriented. And classifier is basically to classify 2 types of data. Yeah. I think I should stop here. I'm not completed. I'm sorry, I not managed my time well. 4 more slides I could have explained slowly. It's time for you. Thank you for it.
Yes, sir. You can take another 15 minutes, sir. No problem. 10:45.
Oh, beautiful. Thank you, sir. You asked me to stop at 10:20, so I'm a little worried.
No, sir. 11 only the inauguration will start.
Oh,
Better we
great.
can- before 15
Oh,
minutes we
thank
will
you.
leave.
Thank you. Thank you so much, sir. Then it's
Okay, sir. Thank you.
okay. Okay, so what does basically classifiers do? Let's take a two-dimensional problem that we can understand it better. We have the data points. I have collected, elephant and cats. Cats are small in size. Let's say x-axis is size, or y-axis is weight. So smaller weight, smaller height, class A. That belong to a lion or tiger or something like that. The weight and height is more for elephant. So the red color data points represent elephant. We want to classify these two. Okay, very clearly these data points you will be able to classify. Unless some baby elephants, which will be in the size of tigers and elephants, tigers and lions, all other grown-up elephants will clearly fall in the red region above. And all lions and tigers will fall in the below region. So the data points representing x-axis representing height, y-axis representing the weight. If you take only two dimension, based on that, you will be able to classify whether we don't have to give any pictorial information. You have an animal, you take the height of the animal, you just take the weight of the animal. With those two information, I may be able to classify that it is a lion or it is a elephant. Okay. Assuming my population has only elephants and lions. Okay. So now I will be able to classify. So what I need to do, I visualize this like this as one graph. There is a classifier separating them. And as the data points are falling apart from that separating line, it is easy for me to classify. Okay, that's the classifier's job. It's not blue moon every day. Sometimes the red color data may fall below, the blue color data may fall above, and they are called misclassifications. They are called misclassifications. So when you have misclassifications, you may have your job becomes tough. It's not linearly separable. Here it is linearly separable. You have a linear line separating the group A and group B. Whereas here, it's not so. The case is worse in this particular slide. You see, the blue dots and the red dots are all mixed up together. You may find it is not linearly possible. You cannot draw a line and then say above which it is a blue class A, class 1, below which it is class 2. You cannot say. Okay, apparently it looks like this with two features. The feature 1 is x1, feature 2 is x2. Okay, with that it is not possible. We are all mechanical engineers, most of us, I suppose, I assume. So it's easy for us to visualize. We might have learned in engineering drawing. You see, there is a three-dimensional vessel. A part of that, the bottom portion of that is filled with the red color dots, and there is a visible, transparent separating layer I put, pebbles, blue color pebbles I put. When I look from top, it will look like this, as if they are all mixed together. Whereas in 3 dimension, when I look like this, the x-axis, y-axis and z-axis, all these three informations are available, then you can find a linear separating plane. It may not be a line, but it is a plane because it is 3 dimension. If it is 4 dimensions, 5 dimensions, because each column of value is representing 1 dimension, I can have even 1000 columns, so 1000 dimensions. So anything beyond 3 dimension, we call them as hyperplanes. And that's also, the visualization is like a plane only, but we may not be able to visualize hyperplanes, but that's an extension of that idea. So you will be able to separate in 3 dimension, which you cannot separate it in 2 dimension. That means more the dimension, it is easy for you to linearly classify. Okay, fine. So I keep increasing dimensions. I take measuring too many measurements. That becomes a problem. What is the problem? Computationally, it becomes difficult when the dimensionality of the problem increases. So I should have as many smaller number as possible for classification algorithm to take fewer hardware requirement, the computational resources. If you make more dimensions, the processor takes more time to compute and tell you. Each dimension you reduce, the processor becomes more and more efficient. Whereas each dimension you add, it is easier for you to classify. So you have to optimize the number of features such that the number of features is sufficient for classification. Also, you are able to do classification well. That's how the research in this particular machine learning approach to fault diagnostics, they are classifying a good condition and faulty conditions, each one treating as a class, is possible. Very easy. I'm going to demonstrate it in 2 minutes time. It's easy, but the difficulty comes in optimizing and these parameters to suit a particular problem. Your research, if at all you are planning to do in this particular area, is all about defining new features. With the extracted features, identifying the good features. With identified features, tuning the parameters of the algorithm to suit this particular problem are all going to be your challenges, research questions which you need to answer. When you answer, people will appreciate your work. And okay, so that way, what is not possible linearly classified in 2D, you are able to do it in 3D. The decision tree is an algorithm. We are not going to discuss. If you want, the recorded lecture is available. You can go. So the formal PPT presentation, I'll stop here. There's a demo that I would like to give. I don't know whether I can do that. Let me see, sir. Presentation. There is a software called WEKA, W-E-K-A, WEKA. You're able to see this window, sir?
Yes, sir. We can able to see, sir.
Yeah, beautiful, sir. There's a software called WEKA that's used for machine learning. For most part of my research, I have used only this tool. It is a free download developed by Vaikota environment for knowledge exploration. Anyone can use. In 5 minutes, you can learn. So essentially, you have to open a particular file in CSV file format. Okay. The CSV file means comma separated version file. Any Excel file, you can say save as and put it as CSV file format. So you save such file. I have opened it already. So open such a file and you have all these parameters here. I have vibration signal from bearings, good bearing, inner race fault, outer race fault, inner and outer race fault. From each condition, I have taken 100 signals, 100 vibration signals from good, 100 from inner race fault, 100 from outer race fault, 100 from both inner and outer race fault. The different colors of the bars represent the number of that particular. From each signal, I have extracted these 13 features. Mean, standard error, median, these are all going to be my features. And last column, which is ticked, is the class. That class labels are going to be either good, IRF, ORF, IORF. That means I have modeled my condition monitoring problem as a machine learning problem. Now I am going to learn using this data and with the learned data, in future I will be able to classify the future data. Okay, how to learn, how to train an algorithm? Let's see. You first tab is pre-processing. There you go. Open your file. Choose whatever the CSV file that you want to. I have chosen new all CSV, and that's what is loaded here. And then you go to the second tab, classify. Go to choose the classifier. You have so many classifiers, so you can write so many papers. Each classifier is essentially a paper if you know how to write it. So you choose these files. I have chosen J40. That's my favorite algorithm. So I have chosen the algorithm, and these parameters are shown here. Now, simply all I have to tell is start. Okay, the data set is fed in, and the classification accuracy is 50%. Probably you vary this parameter. There are two parameters for this algorithm, C and M. You vary that parameter, you will see that there is a change in the parameter. Here 60%, 50%, and so on. So here you get your classification accuracy. and you vary your parameter C and M in order to get high classification accuracy. Now, one more information that you will get from this particular J48 algorithm is like this. What is that? Sir, please mute yourself, sir. If the mean is less than 0.022 and is greater than minus 0.24, then the condition is good. And if the mean is less than minus 0.24, the condition is outer race fault. If the mean is greater than 0.02 and maximum value, maximum is a statistical parameter. So that parameter is greater than 0.06, then condition is good. If maximum is less than this, the condition is IORF. If mean is between these two values, the condition is IRF, inner race path. What I give is an Excel file of 400 rows, each row representing one signal. Okay. The output is the structural information. With 400 values, 400 files or 400 signals, I will not be able to tell this. Whereas once I use J48 algorithm, I get the structural information. What is the structural information? First parameter, if that is less than this, second parameter less than this will be the condition. If first parameter is less than this, the second parameter is greater than this will be the condition. That kind of structural information I will get. Using C or any other programming language, I can simply write that algorithm and then do after the learning process. That's the beauty of learning. Second, the J48 algorithm can also be used for feature selection. You see in the inputs, are given 13 features: mean, standard error, you see, mean, standard error, median, mode, standard deviation, sample variance, and so on. You see there are 13 features. But after classification, you see in the decision tree, there are only few mean and maximum, only the two features that contribute for the classification. When the system parameters are C is equal to 0.25 and M is equal to 50. Similarly, you will be able to choose the features which are contributing to the most by using decision tree algorithm. So decision tree J48 algorithm can also be used for feature selection and classification. There are other classifiers, many of them. They can be used as classifiers only. So using that, you will be able to classify. And now, if the system is visible, okay, I don't know. There is something called confusion matrix that you should be able to read. Each row representing a particular class. See, the first row belongs to good class. I have 100 signals. Out of 100, 62 is correctly classified as A only. That means good only. I have good class. I have fed 100 signals. Out of 100, 62 is correctly classified. There is no misclassification as B. Out of 100, 22 is misclassified as C. C is ORF. Out of 100, 16 is misclassified as D. So these are all misclassification details. Similarly, second row belongs to IRF signals. The IRF signal, no misclassification. All 100 signals correctly classified as B. B means IRF. Okay. Third row belongs to ORF, and 39 is correctly classified. 32 is misclassified as good. 29 misclassified as IORF. Similarly, out of 100 IORF, 40 is correctly classified, and these are all misclassifications. Like that, no, you will be able to interpret confusion matrix. Also, this is the detailed accuracy by class. For each class, what is the TP rate, true positive rate, FP rate, precision, recall. These are all statistical measures, ROC area. These are all some of the measures for standard machine learning algorithms. Once you learn more about it, you will be able to use these values, write detailed results and discussion, and present your work. Okay, so I want to give some time for question and answer. In case if you have any questions, so you can ask. Otherwise, we can stop.
Sir, is this vector software is available freely in online, sir?
Yes, sir. It is a free download. Anyone can download. Also, it is available for Windows version and Mac version.
Okay, sir. Okay. It is only for bearing classification or any other vibration signal also we can classify, sir?
No, sir. It is applied to any field.
Any
The
field.
60 different machine learning algorithms people have implemented and kept. Anyone can use it for any application, not just machine condition monitoring. They have developed it. There are computers, a group of computer science people developed these tools in Java. And since we may not know Java, we just use those tools and make use of those algorithms.
Okay, sir.
Sir, is it possible to change the algorithms for the classifiers using this software, sir?
There is user-defined tools, user-defined classifiers that you can upload, provided you know how to write your algorithm in Java. You can write your own program, upload it, and you can classify using that software.
Sir, how to select the classifiers for the various purposes?
That is what I told you. You have more than 60 classifiers. Which classifier will perform best for one particular application is not, nobody knows, nobody can answer. That you have to use all 60 classifier with one particular feature and find out which one is performing better. That's part of your research. That's a part of a research question. I have worked with 5-6 systems. None of these systems had best feature classifier combination as same. Bearings, my own PhD work. I have finished 7 PhD scholars. Each one different components. None of their final results is same as mine. Mine, I think it was discrete wavelet transform feature with proximal support vector machine was the best combination which performed very well. Whereas for centrifugal pump, the classifier which performed well was different. For breakfall diagnosis, it is different. For single point cutting tool condition monitoring, it was different. So no one can answer. That's the advantage for us. That's why we are able to do research and publish papers. If that standard answer is available, hey man, use this application, use this classifier for all your fault diagnosis problem, you will have only one paper. After that, we can publish papers. Now, because no one is able to tell that, and we do extensive computational work and find out that which algorithm, many people are getting PhD and we are getting some papers.
Sir, there is one more question. How
Yes,
to
sir.
differentiate conventional machine learning and deep learning, sir?
Conventional machine learning requires explicit feature extraction. Deep learning, the deep learning by design, it's actually basically it is a neural network. First, certain layers they use feature extraction by themselves, and the deep learning is developed for mostly for image processing. So from the image, features are extracted first and classified in the last few layers of the neural network. They have integrated feature extraction and classification together and called it as deep learning. Machine learning, you have to extract features by yourself. You have to feed it to the algorithm that we did, like CSV file, and you have to get there. You simply give input data. You simply say this folder is good signal, all photos. This folder contains faulty one, all photos. You simply give it to deep learning algorithm. The deep learning algorithm will extract its own features, classify, and finally tell what it has learned, how it has classified. The final classification result will tell. So that's deep learning. Implementation wise, they are all extension of just neural network. There's nothing new in that's a machine learning. In neural network, we give features manually. In deep learning, the features are extracted by the algorithm itself.
Sir, Sugumaran sir, okay sir. Thank you sir, we are running short of time already.
Yes sir.
Thank you very much.
Thank you so much, sir. Thank you for the opportunity given, sir. I thank all the participants for their patient learning. I'm sorry I couldn't manage my time well. I thought I have enough time, but then I rushed in certain places. Thank you so much.
Very fine, sir.
Have a wonderful learning session. Thank you, sir.
Okay, sir. Thank you very much, sir, for giving a wonderful lecture on the topic machine learning for fault diagnosis. Really, the participants can benefit among this, and they know the new software, the VECA software. I am also new about it. Thank you very much, sir, for your participants.
Thank you, sir.
Participants, you can join the inauguration session. The link is given in the chat box by exactly 11 o'clock. Thank you, sir. And also participants are requested to fill the feedback form which is sent in the chat box.